Get up, get up, get up, get up, get up, get up. Yeah, there it is. Nice.
Hello and welcome to another one of these ADD videos. Today we're going to be looking at the concept of work. What is work? Well, we can look at it in the traditional sense as some force being applied to an object making it move in a linear direction, and it would be the amount of energy required to move that object of whatever mass that distance. We're also going to look at it in terms of kinetic energy later on, but for now let's delve into this formula here. Work is going to be the dot product between the force, and this is the net force. It's the net force dot the distance it travels. So dot product implies a cosine of the angle between the force and the distance it travels. Okay, so that says anything that's perpendicular is not going to count. We're only looking for parallel forces. So anything that's 0, 180, we're good. If it's 90 degrees to the motion we're taking, work will be 0. Keep that in mind. The SI unit is 1 joule, and a joule is 1 Newton meter. Again, reiterate, only the parallel components of force will have an effect. Anything perpendicular will not. This is great for a lot of the Newton's laws problems we just did. If we do a work approach to them, the whole system becomes a lot easier. We can ignore anything that's perpendicular to the path traveled. We will redo some of the problems we did before using Newton's law from a perspective of work. Again, we're going to try to find the net force, multiply it times the distance it travels. Okay? And if there's an angle associated, plug and chug. If the force is in the same direction as the motion it travels, then the work is positive. If the force is in the opposite direction as a motion travels, then the work is negative.
Get up, get up, get up, get up, get up, get up. Yeah, there it is. Nice.
So as I mentioned earlier, we can approach work from a perspective of kinetic energy. So we know that work is also a change in kinetic energy. We see that illustrated once we know the kinetic energy formula. In case you forgot what the formula for kinetic energy is, it's 1/2 mv squared, where m is the mass of the object in kilograms, where v is the velocity of the object, usually in meters per second. So we know that work is going to be the change in kinetic energy as stated previously. So this is delta, the Greek letter, uppercase, usually means change, sometimes heat like in chemistry, but change is always final minus initial. So we have 1/2 mv squared, and this is the final velocity minus 1/2 mv squared with the initial velocity. Oftentimes the object will start at rest, so this whole kinetic energy 1 will go to 0 because v1 will be 0. So work would just equal the ke2 in that scenario. So we can also look at work from the perspective of potential energy. Work will be the negative change in potential energy. So again, change means final minus initial. But remember, it's negative. So what you're going to end up doing is distributing the minus sign through, and then the h2 term becomes a -1, and then the h1 becomes the +1. Don't worry too much if you don't understand potential energy. You'll have to check out the kinetic and potential energy videos and conservation of energy to fully grasp this. But I just kind of wanted to get you ready for what you're about to see and how we're going to use work when gravity is the only force acting on it. We can use this relationship to come up with the conservation of energy theorem. We'll also see how it is affected if a force other than gravity plays in the system. All right? So I hope this has opened your eyes to what work is, and you have enough confidence to try a few of the problems. Make sure you check out the beginner, intermediate, and advanced example videos. And the most important part of your education is for you to practice as many as you can on your own. Tutoring is fine, videos are fine, class and reading, but you got to be able to apply that knowledge, okay? Thanks for checking the video out. I hope you enjoyed it. Have a great day.